All right, welcome back, everyone. Very good evening. And we're back with miniature number 8 this evening, which is about packing complete bipartite graphs. It's, if you like, a problem in graph theory. Goes back to a theorem of Graham and Pollack, which was originally inspired by a communications system problem. And there is this nice paper that's kind of linked to in the slides if you want to go and look that up for the source. But I'm going to borrow from a different YouTube video that I saw about this problem to set it up. So in some sense, the terms that I'm going to use will probably not match up with the original motivation. So it's going to sound maybe a little bit random. And to be honest, I was a little bit um, undecided about whether I want to use this particular way of describing the problem given the current situation of the world. But let's just go with it because it's a nice way of it's a nice way of thinking of the problem as a puzzle. So here's a funny kind of question to think about. We want to know how many battles need to be fought in order for every pair of nations to have fought exactly once. So let me tell you what I mean by that. So with this picture, let's assume that every dot represents a nation. And a line between the two dots tells you that those nations have been in a head-to-head fight. Maybe a nicer way of thinking about it is, that these dots represent players or teams in a tournament, and an edge between them represents the idea that they have faced each other off. So, for instance, in the current phase of the Cricket World Cup, you have, okay, I don't know how many teams we have. Do we have 10 teams? Or something like that. So you have 10 countries. And I think just going by how many matches there are, seem to be never ending. I'm assuming everyone's playing everybody off once, right? So all those pairwise connections kind of emerge in this representation. But then the question I want to ask is, I'm trying to imagine how these fights happened. And well, it could be that every nation engaged in just a personal battle with every other nation, but it could also be that there were battles that were fought that led to these one-on-one fights. So by a battle, I mean a group of nations fighting another group of nations. So here you can see hopefully that the if you just focus on the red edges, and I think there's a way that I can do that. Yes, so if we just focus on the red edges, we see that we leave out the nation that's at the bottom right corner, and if you look at the three nations on your left and the two nations on the right that are highlighted, it's basically these two groups going, colluding and going against each other in a battle. So we assume that in a battle, all the nations on one side fight with all the nations on the other side. That would be one battle. And I'm trying to understand, well, what's the smallest number of battles that could have been fought to account for all of these individual fights between the nations? Is the difference between a battle and an individual fight clear? Like in terms of terminology, just give me like a +1 or a question mark in the chat. A question mark if you want me to repeat, and a +1 if you think it's okay. All right, maybe I should just repeat myself. All right, so a battle is a group versus a group. Yeah, it's a clash of nations. So it's multiple nations going against each other. So imagine that they're allies, they group into allies, and there are, a battle still has just two groups, which are just going in a head-on collision against each other. So everybody from one group fights everybody in the other group. A fight is a special case of a battle where you just have two lonely nations fighting against each other. But yeah, fight would be an individual. You identify a pair of nations and they're at war. That would be a single fight. And a battle is when you have a group facing off a group, by which I mean that every person in one group faces off every person in the the other group, or every nation in one group faces every nation in the other group. Okay, I'm glad. So let's look at a few other battles which could have potentially happened. And notice that we are given that every nation fights every other nation exactly once, which means that a pair of nations could not have been involved in more than one battle where they're facing off each other, right? So let's go ahead and look at some other potential battles. So here is the set of green edges accounting for these guys, and then we have just that a very simple battle between just one pair of nations. Here's one where two nations are ganging up on one. And here's the same situation. You have two nations ganging up on one. But that accounts for all the fights. So these are all the different battles that may have happened. And you notice that there are, well, let's see. It appears that there are 5 of them. And there are 6 nations, right? And the question we want to think about is, okay, what's the most efficient way in which all of these individual fights could have happened? And by efficiency, I mean, what's the smallest number of battles that can account for all the fights? And let me just head over to sort of a GeoGebra thing. I'm just wondering, can we try this out in real time? Like, do you want to maybe, the challenge is, can you do it with, oops, I don't want more than 6, but let's see. Maybe we can try to collectively see if we can do it we have already seen one way of doing it with 5 battles. Maybe can we improve it to 4, for example? So any suggestions for, if you're trying to, maybe we can try to be greedy and do one battle that accounts for a lot of edges. What is, like, to start with, we have a blank canvas. So with one battle, what's the maximum number of edges that we can account for? So for example, if I have A, B on one side and a C, D, E, and F on the other, how many edges would that account for? Okay, I'm already using the word edges. By edges, I simply mean those lines or individual fights. So a battle between A, B on one side and the remaining 4 countries on the other side would account for how many individual fights? That's the question. Okay, that would account for 8, exactly, because you have 2 on one side and 4 on the other. So each of those 2 fellows fights with 4 of the nations on the other side. So that would be 4 plus 4, 8. But in general, it's just going to be the product of the size of the group on one side and the size of the group on the other side, right? So that's what it's going to be in general. So if we have, let's say, one nation being attacked by all the remaining nations, that's a different kind of extreme scenario. So let's say everybody gangs up on A. That would account for how many edges, or how many of the individual fights? Okay, that would account for 5, because that's if I were to draw them out, you'll get all of these individual 5 lines. By the way, let me make sure I have annotations enabled today. Just give me a moment. Okay, so I think annotations should be enabled now. So feel free to, if you want to draw along. I mean, I'll try to carry out in GeoGebra what you ask me to do, but in case that's tiresome and you just want to draw yourself, feel free to do that. Okay, so maybe let's give this a shot. Let's not overthink it. Does somebody want to give me a first battle? And then we'll just see if we can accumulate all the edges in 4 of them or 5 of them, or maybe even more. I mean, it may turn out differently on how depending on how we decide to go about this. So I'm not overthinking the optimization at this stage. Let's just try to get a feel for the problem. So somebody propose a battle. I'll take the first one that comes up in the chat. Okay, let's do 3 versus 3. And at this point, it doesn't really matter which 3, because it's kind of symmetric. And maybe you're saying 3 versus 3 because you took my comment about maximizing how many of these fights I can account for kind of seriously. That would be optimal because I get 9 out of doing 3 versus 3. So the 3 versus 3 that I'm doing are A, B, F versus C, D, E. Again, I should probably color these in some way to remember. I don't know if there's a way of doing this more efficiently. Okay, any GeoGebra users know if I can select more of these at once? Maybe I should have just left it at black, but okay, never mind. Okay, in the meantime, somebody give me a second battle while I'm painstakingly coloring these in. Okay, whom should we have? Okay, 2 versus 4, but now you have to tell me which 2 versus which 4, I think, or okay, can we do 2? Okay, let's see. Can we do 2 versus 4? So we have AF, for example. Okay, 2 versus 4 seems a bit tricky because remember, every pair of nations engages in a fight only once. So in particular, we cannot have any of these groups. Like for example, I cannot separate A and D anymore now, right? Because that would mean that they're going to fight again. But that's not happened. According to our records, every pair of nations is fought only once against each other. And we are trying to account for all those fights by a decomposition with battles. So I could do, for instance, AF and AB, but I cannot expand on that anymore. Does that make sense? So let's see. If I try to do 2 versus 4, let's see, which 2 do I want to fix? Maybe I want to fix. So the 2 better be. I don't know if they better be, but if I pick AC to be the 2 nations that are on one side now, because they can't be on opposite sides because they've already fought. So now they've patched up and become friends. So AC on one side versus, let's say, the rest of the world. So A goes against F, A goes against B, but C cannot go against B or F because C has been there, done that. So C is not going to do that. So this cannot be the case. In fact, if I choose to put A and C on one side, I don't think I can draw any of those battle lines, right? Because whoever C is open to fighting with, whoever C has not fought before, A has fought before. So A and C cannot fight them simultaneously. And the same is true of A. Is any of this making sense? Yes, I'm trying to explain that 2 versus 4 is going to be a tough. No, so these edges are undirected. So normally you would have a direction to encode something like who won the battle. So you'll say that A is the line going from A to B is pointing towards whoever won that battle, for instance. But right now we're not really interested in the outcomes of the individual fights. Those are very interesting questions that usually come up in tournament analysis. And in fact, the class of these objects where you have all the lines going between all the points and they all have directions, these are literally called tournaments, and the entire book's written about them. So there's a lot going on there, but that's a little bit out of scope. So we're going to, here we are just keeping track of which pair have engaged in a feud, and we are trying to decompose it in terms of what we are calling battles, right? Okay, so at this point, 2 versus, okay, so let's see, let's analyze the possibility of, 2 nations going against 4 or going indeed against anybody at all. So if I try to club together 2 people who have already fought before, like AD or CF or BE or any of those, if I take any of this sort of a cross pair and try to make them have a common, have them engage in a battle where they're both fighting a common enemy, well, I don't know that I can find a common enemy for any of these. So for example, if I fix B and C, well, A cannot be fought by both B and C because C is already fought with A. D cannot be fought by both B and C because D is already fought with B, and so on and so forth. So you're going to run into trouble. So you cannot have, the 2 people coming from opposite sides of the first battle. So let's see if A and B can fight somebody together, for instance. So if I group A and B, well, they've already fought C, D, and E, so that's not happening. But possibly they can fight F. So I suppose we could do that. And that would account for 2 more of the fights. Should we freeze this? This is fair. I think this can happen, but nothing more can happen. Like A and B will not be fighting E, D, and C because they're bored of doing that. They've already done that. Is this okay? So let's take this as our second battle. Okay, so that accounts for 10 of these battles, and we have, how many do we still have left? Okay, E and D can pair up pretty much the same way that A and B did. Not in the same, so that will be a fresh battle. So let's do E and D. And yeah, there are 5 edges left. Maybe we can even see which 5 edges are left, or which 5 pairs are left. C, E, this triangle at the bottom, C, D, D, E, and C, E are left. And then A, B is left. What else is left?
9 plus 2 is 11.
9 plus 2 is 11. So yeah, so plus 4 is 15. We have 15 edges to begin with, right? So I think we are good. The triangle plus the single edge. Thank you. So let's go back to pairing up E and D. So maybe pick up a different. Let's make that purple. And now we really don't have a choice anymore. We cannot account for both ED and AB, both of those missing fights, cannot account for them simultaneously. Like, so we could say, well, what if AE and BD group, like AE is one group and BD is one group? But then notice that if you fight that battle, then A would have to fight D and E would have to fight B, but those battles have already happened. So we can't make them happen again. So we are really at this point compelled to make these 2 separate lonely sort of battles. Okay, so that's what's going to happen if we push along these lines. And you can play around with this some more and try and come up with, other ways of distributing these fights across battles. But it'll turn out that no matter how you do it, and there are many different ways of doing it, and I think that's another interesting question to think about, like in how many ways can you decompose these 15 individual fights into some n number of battles. So another extreme is that you don't care for optimizing for the number of battles. You can just say that they were spread across 15 individual battles over time. But this one is you sort of really, push these fights into larger battles. And you said, well, all the 15 fights transpired over these 5 battles, and there could be multiple ways of organizing them across 5 battles, maybe 6, 7, and so on up to 15. So that's a counting problem, but again, I'm afraid that's going to be a little out of scope. We're going to come back and talk about, well, what is the smallest number of battles that you can organize these fights into? So in this case, well, we did it a couple of different ways. I think what we did is strictly different from this example here because I don't have anything which has 9 edges, but that's where we started. So just to be consistent with the terminology in the miniature, I'm going to just talk about what these things are called. So what we have here is called a complete graph on n vertices, and we are trying to we are trying to cover the edges of this complete graph using what are called complete bipartite graphs. So complete bipartite graphs are these pieces, these battles, or these groups that we were trying to form. So in terms of graphs, if you've already seen graphs before, this probably feels familiar. But if you haven't seen graphs before, don't worry too much about it. It may just be useful to get familiar with the terminology when you have some time offline. Okay, so essentially, we are trying to cover this whole thing, which has n points and n choose 2 lines. The lines I will often slip up and just call them edges. You're trying to cover this using a combination of these structures where you have P points on one side, Q points on the other side, and you have P times Q lines that join all of these points, right? So you're trying to sort of patchwork your way into covering all the edges in this object with a bunch of these kinds of smaller objects, okay? And well, the claim is that if you start out with n nations, then you need at least n minus 1 battles to account for everything. So we started out with 6, and the claim is that you can do no better than 5. If you try to accommodate for everyone with less than 5 battles, then you're going to sort of run into some kind of trouble. So that's kind of the idea. Let me just maybe quickly as a warm-up do a related question where I ask myself, how many connections do I need to just get everyone to have a connection, direct or indirect, with everyone else? Sorry, I'm kind of a bit slow getting rid of these connections here. So now let's just change things a little bit. It's just a 2-minute detour. Let's think of these points as representing people. Okay, so A, B, C, D, E, and F. And I have a connection or a direct line between two people if they're friends. Okay, so if they know each other, and often you do this thing about, well, I know somebody who knows somebody kind of thing. So I want to add just about enough lines so that everyone knows everyone directly or indirectly. If you want everyone to know everyone directly, then there is nothing much to be done. We just have to go back to the previous picture where we just throw in all the lines that connect everybody. So that would be 15 lines. But if I'm okay with having to go through someone and then go through someone else and establish an indirect connection, I'm still happy with that. I just want to make sure that, for example, the situation is not like this, say. Now, is everyone connected with everyone here in this picture, directly or indirectly? So for those of you who do know graphs, I'm just asking for the minimum connectivity requirement. What's the smallest number of edges you need to have so that your graph is connected? And the answer is indeed n minus 1. For example, here I've actually thrown in more edges than I need to, so I could get rid of one of these still. You can see that, for instance, A and D here are isolated from B, C, E, and F, okay? What do I need to do to make this connected? Well, in this case, I can just add one of these edges and I would be sorted. In general, what's happening is that, well, every time, so to begin with, I have 6 groups, and whenever I add a connection between, so 6 groups that are completely isolated, okay? So everyone is their own island. And whenever I add one connection, I reduce the number of groups by 1. So now A and D are now, I can think of them as a sort of a meta person because they both know each other. And I'm just trying to make sure that everyone's kind of ultimately connected to each other via these connections. Every time I add a connection, I drop the number of groups by 1. And I want to get to the point where I have only one group. And I start with 6 groups. So with every line that I'm adding, I'm reducing the number of groups that I want. So as people are pointing out in the chat, you have, by the time you've added n minus 1 of these lines, you would actually be done. So I think there's a comment about a bus. I'm assuming that's some sort of a network topology term. I'm not very sure. So you could do this sort of thing where you have a central hub that's connected to everyone. This, I think, is called a star, but there could be other ways that you do this as well. And you can formally prove these things using some kind of induction argument, saying that if you know that it can be done for n with n minus 1, then for n plus 1, you need only n, and so on. So there are different ways that you can do this. And in fact, in a later miniature, we will actually talk about this counting problem of in how many ways can you get these connections going. But okay, that was an aside. Here we are looking at a slightly different problem, but it does help to think of, in some sense, the groups as meta vertices that you're trying to connect. I'm honestly not sure if the intuition from the detour is immediately helpful, but I will link you to a YouTube video where there's a slightly different proof of the same fact, which actually builds on this intuition in a more direct way and probably reveals where some of the linear algebra magic is coming from. Now, in the last 5 minutes or so, I will try to give you the proof that is in the miniature, which frankly feels very magical, at least to me. But hopefully in the follow-up resources, there's a little bit of a shedding of light on what's exactly going on. Okay, so let's get to what we are trying to prove. So, okay, is the statement okay? Is the statement of what we are trying to prove clear? Give me a +1 if we are doing good on that. Or if anything needs to be clarified, I'm happy to spend more time on that. Okay, so if it isn't a +1, which is understandable if that is the case, but then let me know what you want me to clarify.
Everyone is quiet. Huh?
It looks like I'm wondering if somebody's maybe typing out a question. And by the way, if it's easier, feel free to unmute yourself and just ask. That's fine too. Or if you have a comment, that's cool as well. Yeah, I'm going to be in a fix if I get no confirmation and no complaints, because then I okay, all right. Thanks, Joel. Okay, all right. So yeah, thank you. So yeah, basically the idea is that this process that we worked out for accounting for 6 nations with 5 battles, 5 was basically the best that we could have hoped for. That's the claim. And of course, the statement is in terms of generally speaking, n nations. And okay, is n-1 always achievable? So that's a great question. I'm going to leave that as a little bit of food for thought, but you could try to either generalize from one idea is to start from some kind of a star where one nation gangs up on everyone else, and that accounts for n-1 of the edges. And then, well, you have that nation kind of accounted for, all the fights that that nation was involved in is accounted for. Then you could do a star rooted at a different nation fighting, ganging up on everyone else except for the first bully, the first victim nation, actually. So when you have a star, it's basically all nations ganging up on one. And then you have that pushed out of the picture. And you can essentially repeat this construction with smaller and smaller stars and see if that helps and if that gets you somewhere. Or you could try to do what we were doing when we were chatting earlier, where you try to go greedy and you say, I'll try to maximize, I'll try to split it into 2 nearly equal halves. Here we manage 3 and 3. If it's odd, if it was 7, it would have been like 3 and 4. You try to start there and try to greedily pick up a lot of fights in one battle, but then you will see that you get more and more constrained and your future battles will have to be smaller and smaller. But it's a nice exercise to try and make any of these kind of intuitive approaches more systematic, and that will hopefully lead you towards an answer for your question. Okay. All right. Since no one's complaining, I'm going to probably move on. Yeah, of course. Thanks, Karthik, for that question. And okay, so with the confirmation from Joel, I'm going to move on and try and convince you that indeed I only have, okay, I'm going to probably spill over a little bit on time, but let's hope that it'll be worth it. So what we are going to do is suppose somebody has given us M of these battles. Okay, so M complete bipartite graphs that supposedly cover all of these individual fights. And the disjoint objective is to say that, well, no nation fights more than once, right? So every fight or every edge occurs in exactly one of these complete bipartite graphs, right? So they fight once, but not more than once. So that's what it means to disjointly cover. And now we're saying, well, for HK, let XK and YK denote the 2 groups of nations that were warring in that particular battle. Okay. And notice that in an individual battle, you may not have involved all the nations. That's what it means to say that, if you look at everybody who was engaged in a particular battle or all the vertices of a particular complete bipartite graph in this decomposition, that may not account for all the vertices, and that's fine. You just want to say that it's a valid battle, which is you have a group of two subsets of vertices that are disjoint and everybody goes against everyone. Okay. Now let's draw up this matrix associated with an individual battle where we say, okay, let's index it's an n by n matrix. Okay. And I'm going to say, well, let's highlight one of the groups on the columns and one of the groups in the rows. So here, for instance, I have one group of nations being 2 and 3 and the other being 1, 6, and 5. And then I'm going to basically throw in ones at the intersection of these highlighted rows and columns. So is the matrix associated with a battle okay? We're basically saying on the rows, shine a spotlight on all the nations involved in one group. On the columns, okay, I don't know what I said first. But on the column, shine a spotlight on all the nations involved in one side of the battle. And on the rows, shine a spotlight on all the nations involved on the other side of the battle. And then wherever these spotlights intersect, trigger those matrix entries to ones and everything else to zeros. Okay, that's the matrix. Does this matrix construction make sense? And hopefully the example is helpful. All right, so that's what we have. We developed.
Yeah, but it seems to depend on which
side.
It's not symmetric, right?
Yeah, it's not symmetric. So for example, so basically I'm going to arbitrarily fix the row column, the row column conventions, because what we're actually going to deal with is we're going to take this matrix, take its transpose and sum it. So then that's going to get rid of the anti-symmetry. So, I mean, ideally, if you went the other way, the starred entries would be the ones that were highlighted. So if you changed your convention for, what goes on the row and what goes on the columns, you would have gotten the starred entries being 1 instead. So that's basically the transpose of the base matrix with both. And it's useful to keep that in mind. So yeah, why isn't 2, 1, 1? That's the reason. Yes, thanks, Joel. So all right, so yeah, this is a slightly arbitrary convention. We can just fix some convention for every HI. Fix the group that you want to represent the rows, and the other group will represent the columns. And you build out these matrices, and we'll eventually get rid of this asymmetry anyway. But for now, what's useful is for the base matrix. Notice that this is what's the rank of this matrix? Anybody? That's well, we have a whole sea of all 0 rows, and the remaining rows are essentially the same. Okay, so this is, we don't have the starred entries, Joel. We just have this, right? So it's going to be all zeros for the most part, but all the non-zero rows are exactly the same. So it's a rank 1 matrix. Are we happy with that? The claim that this is a rank 1 matrix? Without worrying about the transpose, right? Okay, so perfect. So this matrix AK is a rank 1 matrix. And we are now going to consider the sum of all of the matrices that we get from all of the individual battles. And because we are summing M rank 1 matrices, the sum has rank at most M. And now we are going to show that this matrix, which is the sum of these individual matrices, has rank at least n minus 1. If we do that, we are basically done, because the rank of A on the one hand is at most M, and it's at least n minus 1. So M is at least n minus 1, which is what we wanted to show. We wanted to show that the number of battles in this decomposition is at least n minus 1. Okay, is this plan of action reasonable? Can we now just focus our energies on showing that the rank of A is at least n minus 1? Give me a quick +1 in the chat if this looks fine. All right, awesome. Thank you. Okay, so moving on. Now remember that this matrix A is the sum of all of these individual matrices with arbitrary assignments of rows and columns. Okay, now I should have really split the slide up, but okay, let's just try to take this in. Okay, let's consider A plus A transpose. What is going on with A plus A transpose? Well, each of these individual matrices, when you add it with its own transpose, that basically accounts for all of the battles between all of these groups. in both directions. So we are saying 2 fought with 3 and 3 fought with 2, 1 fought with 3 and 3 fought with 1. It basically accounts for these battles going both ways. And now when I add up, A1 plus A1 transpose with A2 plus A2 transpose and so on up to AM plus AM transpose, when I add up all of that, then I get a 1 in every entry, because I know that these individual pieces were such that every fight was accounted for exactly once, right? So this is addition in R, okay? We're not doing anything fancy. And I'm claiming that you get exactly a 1 in each entry, because pick your favorite entry, well, except for the diagonals, but fix your favorite non-diagonal entry. So let's look at 4 and 5. So there must have been some battle in which 4 and 5 fought each other. And there must have been, in fact, exactly one battle where 4 and 5 were on opposite sides. There's exactly one complete bipartite graph where 4 and 5 were on opposite sides. And now if the base matrix A had 4 on the row side and 5 on the column side, then we are done. But if the base matrix had 4 on the column and 5 on the row, then its transpose would have had 4 on the row and 5 on the column. So either A or A transpose would have captured a 1 in that location. So basically, when you sum up all of these matrices, you get the all ones matrix except on the diagonals. Is this okay? All right, super. So when you add everything up, you get the all ones matrix minus the identity matrix. So this is, so this is something that's useful. We'll remember this. And now we shoot for a proof by contradiction, which is really a small computation, and we'll be done in just a couple of minutes now. So suppose, for the sake of contradiction, that the rank of A is not at least n minus 1. It falls short, so it's at most n minus 2. Now consider this augmented matrix where I've taken A and I've added an all ones row at the bottom. Okay, if I add one row to a matrix whose rank was already at most n minus 2, then the rank of this augmented matrix can go up by at most 1. So the rank of this matrix with this extra padding at the bottom is at most n minus 1. And because this is therefore, so this matrix has n rows and n columns and n plus 1 rows. So if its rank is at most n minus 1, it's not full rank, which means that there's a non-trivial vector in the null space. It's a non-trivial vector that this guy is sending to 0. So let's grab that vector. There is some x such that ax is 0 and x is non-zero. But if ax is 0, then notice that because of this all ones entry, all the entries of xi must add up to 0, right? Because in particular, A acting on x is 0. So the last coordinate of that 0 vector is the sum of all the entries in xi. Are we doing good so far?
So what are the dimensions of the matrix? A itself?
A itself would be a n by n matrix, and this augmented matrix has one extra row, so it'll be a n plus 1 by n matrix. Because the A matrix is the sum of matrices which look like this.
Yeah.
Right, thanks. Okay, so now we are going to remember all this stuff on this slide. I don't know how. I'll remind you about what were the claims we made as we go along. But now we have a simple computation. Let's consider X transpose A plus A transpose X. Let's consider this expression. Remember, A plus A transpose was Jn minus In, all ones except for the diagonals. So we're going to substitute that here and expand this out. Now, what can we say about J and X? Well, remember that the entries of X added up to 0. That's how we chose a non-zero vector X that was being sent to 0. But because we had that all ones row at the bottom, we know that the entries of the vector X itself sum to 0. So this fellow goes to 0. But now the identity matrix acting on X gives you X right back. So you're left with X transpose X, which is a sum of square terms. And remember, X was a non-zero matrix. So this quantity here is less than 0, strictly less than 0. On the other hand, let's just expand it out in the more natural way where we say, well, just take the x inside both of those terms. But we know that A acting on x is 0 because we picked a vector from the null space. So this expression is also 0. So the expression can't be 0 and less than 0 at the same time. And that's our contradiction. So yay, but certainly a distinct lack of intuition for what's going on, at least for me. But okay, in terms of mechanics, are you convinced with the computation? Does anything look shady or anything that's not clear? Okay, clear. That's awesome. Okay, so I think that, I mean, yeah, this does, the mechanics of the calculation, I think, are not difficult to grasp. I think in terms of just validation line by line as to what's going on, everything does seem to check out just fine. And then you get your contradiction. And to begin with, I was trying to see if this is this general idea of a dimensionality argument, trying to say that, well, you're trying to fit too many vectors into too many linearly independent vectors into a space whose dimension doesn't accommodate for it. I was trying to get some intuition from there, but I wasn't sure how to see it that way. So like I said, I will share this video, which I'm still trying to parse, which seems to give a more intuitive approach to the solution and ties it up to solutions of linear equations. So I'm hoping that I can tie the whole thing back to this proof that we saw here. But unfortunately, I haven't digested that enough to be able to present it in that way. If there is a more intuitive roadmap to this proof, that is the one that I would have very much liked to present. But for now, this is what we have, which is basically following the narrative in the miniature. But if I'll, for those of you who have the time to just look at the video, I'm going to share that on the forums anyway. And if I have any new insights, I'll be sure to let you know. In the meantime, any quick questions, comments would be welcome. Sorry for going a bit over time, but I had fun building out the battles with all of you. So thank you for being a sport and playing along. All right, so it appears that we don't have any specific questions or comments. Also, be sure to check out Graham and Pollock's original paper, which makes a connection to, like, this is not just a hypothetical puzzle. It's tied to a real world problem, and I anticipated not having enough time to go over that, but it's definitely nice to check out. So I'll post a link to that in the forums as well. All right. So thanks very much, everyone, for sticking around until the very end. We will be back tomorrow with a geometry-inspired miniature again. Miniature number 9 is about how many equiangular lines you can fit in whatever space. So we're going to come back to that, and then it's back to graphs for a while after that. So we're going to go back and forth between these two themes for the next few miniatures. So see you tomorrow evening. Thanks so much for joining in, and take care. Good night for now, folks.